Okay, good afternoon. Right, so this is going to be the last lecture in the mechanics section, which may be a relief to most of you. I hope you didn't. I know some of you will be disappointed in your test results, but I thought generally people seem to do pretty well in the test. And if you didn't do so well, it's only a test. You've still got the other test and the exam and all the other work that counts towards your final grade. So I think someone asked me whether they had to pass the test, and you don't need to specifically pass any of the tests. You need to pass, well, not pass, you need to do reasonably well in the final exam, about 40%, and you need to also pass the lab part of the course, because that's an important part of the course. So today we're going to finish off energy and work, and next week will be a different section. It will be about waves and oscillations, and then the rest of the course will involve some electricity, some optics, and a little bit of nuclear physics. So this mechanics section is really is by far the longest section in the course. So we've been building this up from the very beginning. We started off with motion, and then added forces, Newton's laws. Then we added momentum conservation, and this week we've been adding energy conservation. So I know it's a lot to take in, but what I hope is that at this point the whole thing will start to seem as if there's some sort of sense to the whole thing of mechanics. If there isn't, I mean, hopefully in a little while there'll be some sense to it. So we're going to talk about potential energy again, thermal energy, conservation of energy, and collisions. And at the end we'll just say a little bit about power. And, oops, I should remember to put the microphone on. So potential energy was the stored energy that could be converted into other forms of energy, and so that included gravitational potential energy. So we say that the ball has potential energy, and when we release it, that potential energy is converted into kinetic energy, and the ball falls. And this is a really powerful way of thinking about many problems. We've done problems where we just kind of drop a ball, and then we've done other problems where we might have a ball on a slope, and we worked out normal forces and so on, worked out what the acceleration is. But by using conservation of energy, we can skip past some of the difficult algebra and go straight to the answer. And we can do that even when you have a complicated situation where maybe it's not just a straight fall, maybe it's like a water slide or something. It has curves in it. We don't need to worry about that to calculate some things. So when we drop the ball, where the potential energy has been converted into kinetic energy, even if things aren't moving, we might, if I have a force on the ball, I lift it up. We're doing work on the ball and increasing its kinetic and its potential energy. And one of the difficulties when you start doing this is to really keep track of what is the system and what is the thing doing work on it. And so here we've said that we have the Earth. I mean, this might seem a little bit artificial, but we're saying that the system is the Earth plus the book, or the Earth plus the ball in this case. And in some sense, we're standing outside the system, applying a force to the system, which includes the ball and the Earth. And that might seem a little bit confusing, and after a while, you don't need to worry quite so much about the system thing. So this is our formula that we've used before for potential energy, and it's interesting. Okay. I'm having this, afraid I'm having the same problem as I had before, that when I switch to a different source on the document camera, it's not coming up on the live stream. It just seems to be remaining. Hang on, I'll just try that once more. Otherwise, we can always try drawing on the picture, but I'm always pretty useless at doing that. Okay. So we have the potential energy, m times g times y. So if we're climbing up the mountain, the potential energy only depends on how high we go, and the force, the mg would be the force if you were just lifting yourself straight up the mountain, which would be hard work, would feel like hard work, but in fact it's all the same amount of work. So this illustrates a really important point, that doesn't matter whether we take this path or this path. When we get to the top, the potential energy is determined just by the height and by gravity and by the force of gravity, the gravitation, which causes gravitational acceleration. So here's an example. So if I have a marble rolling down the steep hill and then down a less steep hill, will it be going faster at the bottom depending on which hill it rolls down? Same speed at the bottom of the hill, okay. So people are saying the same, okay, that's good, because that's what we just said. So because the speed, we can work out the speed by how much potential energy is converted into kinetic energy. There's the same change in potential energy in both cases, so there'll be the same velocity or same speed at the bottom, different directions in this diagram. Okay, so I'm just going to assume that we can't change the slides outside the room at the moment. So we've talked about gravitational potential energy. Another sort of potential energy is elastic potential energy, where you stretch or compress a spring. And that's going to be important in describing oscillations and waves later in the course. And the key formula here is Hooke's law. So this is saying the force is proportional to how far you move and some constant, and that delta x is measured from the equilibrium position of the spring. So if you stretch it, you're increasing delta x, and there's a negative sign here because if I pull on the spring or rubber band in this case, I'm applying a force in this direction, and the rubber band is applying a force back in that direction. That restoring force by Newton's law, action and reaction, is in the opposite direction to the stretching. I don't have a spring to demonstrate the compression, but the compression works in the same sort of way. So it's actually reasonably typical in a physics lab to just do an experiment with a rubber band or a spring and just put more and more weights on and see whether you do in fact get this linear relationship between how much you stretch it and what the force is. So I'm not going to derive this, but if you're familiar with calculus, you can see that potential energy has got something to do with basically integrating the force times the distance. But the point here is that as you stretch the spring, the force gets stronger and stronger, and so it turns out that the potential energy is, I'll try to put the thing back together, otherwise the IT support people won't be very happy with me. Okay, so the potential energy is proportional to the square of the spring. So you stretch it twice as much as 4 times as much potential energy. You can tell that yourself when you're stretching a spring. So here's a reasonably practical application of a spring. I mean, springs are used in all kinds of mechanical devices, but often they're hidden away inside and you can't really see what's going on, whereas the spring here on the bow is very easy to see. So here we're saying that the archer has pulled back the bow 70 centimeters. Sounds about right. That's a little bit less than a meter, and the force is 140 newtons. And if we assume that Hooke's law holds, that the force is minus kx, then we can find the elastic potential energy using that half k delta x squared formula. So k, first of all, you've got to work out what the spring constant was. Remember with the bow, it took a force of 140 newtons to pull the bow back by a distance of 0.7 meters. So you can work out the spring constant. It's the force divided by the extension of the spring. And then having worked that out, you can work out the potential energy of the bow is just a half kx squared, or delta x squared. Half times 200 times 0.7, notice that one's squared, is 49 joules. So we could continue with this sort of calculation. We could say that stretching the spring, the bow, we've got stored 49 joules of energy. If we let go of it, all of that energy, or most of it, will be converted into the kinetic energy of the arrow. So the kinetic energy of the arrow is half mv squared. So by equating the change in potential energy with the change in kinetic energy, we could work out how fast the arrow was going to go. But we haven't actually said what the mass of the arrow is, so we can't actually do that in this point. But earlier on, we talked about kinetic energies of various things: baseballs, raindrops, cars, I think. And so 50 joules, 50 or 100 joules is a reasonable amount of energy for something that you could throw or that you'd use in a bow. In this course, we're not going to say very much about thermal energy, but thermal energy is obviously really important to like living. If we don't have thermal energy, we get too cold and we tend to die or something if the heating stops working. Thermal energy is kind of just kinetic energy of the molecules or atoms inside the substance. Could be a liquid or a gas or a solid. And if something is hot, then those atoms and molecules are moving faster, and that's what makes them hot. That's a whole sort of section of a course to discuss thermal energy properly. But it's good to have some idea of what's happening there. And so it's good to be able to visualize this. If you have a red hot piece of steel, the atoms are moving very quickly. If you've got an ice cube, the atoms are moving quite a lot slower. Lost everything off there. Let's put that back. So conservation of energy. So we're saying that we said before that the change in all the kinds of energy we can think of is equal to the work done on the system. So those are the changes, the deltas, delta, delta, delta. So instead of writing it like that, you could say the total energy after something happens is equal to the total energy before something happens plus the work that you did on the system. So here, I'm not sure why they wrote this. I mean, they've written delta. There was thermal energy on one side rather than the final thermal energy. We could have written that as ETH final and ETH initial would mean the same kind of thing. So remember that example where we were lifting the book or something. We're thinking of the ball and the earth and everything apart from my arm as being the system. So I do work on the ball. That's increased the total energy of the system. If it's isolated, then these don't change. So here's the Here's some examples. I mean, these are examples that we've used before. Objects in free fall. There's the weight, force of the Earth on the ball. The force of the ball on the Earth is equal and opposite, and we're thinking of that as the system. The ball sliding down a ramp. It's not really any different from here. It just sliding down a ramp makes the motion more complicated. But in terms of the, if it's frictionless, it doesn't really make much difference to this. We can compress a spring, and we can have something sliding on the surface with friction. So yeah, notice when we did these sorts of problems before, we were doing things like we'd say, let's isolate the block, and then we say, well, the block's moving with a certain velocity, and there's the force on the block was the frictional force. How did we write that? Let me write it as. I'm just going to write it as force friction at the moment. So when we wanted to work out the force on the block, we isolated the block. Now that we're doing this with potentially with energy, we're saying, well, the whole system in terms of energy is this. That doesn't change our calculation of the force. We can still do that. But there's going to be, as the block moves, it's going to heat up the bottom of the block and heat up the Earth a little bit because of the friction, and so the frictional force is going to do work which turns into heat. Now did we? I think dropped by 5 meters. Okay. Down equations for conservation of energy. So here we're saying that the U plus K final is U plus K initial, and so if we take we could take the initial U as being the height, call that 5 meters, call that Y, YGM, and the initial kinetic energy is 0, and that was Y equals 5 meters. And then after it's rolled down the hill, the final potential energy is 0. The kinetic energy is a half mv squared, and so you can, and so that kinetic energy after it's rolled down the hill is the same as the potential energy it had before it rolled down the hill because of this energy conservation. So this is actually pretty much exactly the same example, except this is a little bit more complicated because we're starting off up at 9 meters. We've called this is y equals 0 down here, 9 meters, and now the child has an initial velocity of 2 meters per second, and then after sliding down the slide, we want to find VF. And as I said before, if we wanted to do this using Newton's laws, we'd be saying, oh, it's kind of flat here, and then now it's steep, and we'd work out the acceleration and so on. That's quite hard, isn't it? I mean, that would be really bad to work out in a test. So we're not interested in that, though. All we're interested in is how fast is she going when she comes off the end of the slide, because, I guess how fast you're going is proportional to how much fun it was. I think that's a physics rule, I think. So we're doing exactly the same thing. We started off with an initial kinetic energy, half mvi squared, an initial that was So that was when she was up there. And the MGYI, that was this one. And then on the other side, the final is down the bottom. And I think YF was 0. So we can work out that the final kinetic energy is the initial kinetic energy plus mg times y. Putting that together. And then we can easily solve that, because this becomes Vf squared is 2 over m multiplied by this stuff, half mvi squared plus mg yi. And of course the m's cancel out, and the 2.5 cancel out for that, so it's just vi squared, but there's still a 2 times g times yi, so that's the final answer. 13 meters per second, so that's it's about around 40 kilometers per hour, so that must be a really fun slide. Unless she doesn't like slides, in which case you're probably traumatizing her by making her ride the slide. So it just depends on the situation. Okay, so that's just summarizing these are the main types of energy we're considering: kinetic energy, gravitational potential, and elastic potential, plus sort of what we'd mostly consider losses, heat, light, sound, right? So when I drop the ball, it doesn't bounce as high as it started, because it loses some of the energy. That energy goes into making a noise. It goes into heating up the ball. If you bounce it enough, if you play squash or something, you know that the ball gets hot after a while. I can find a better or worse ball. So I actually I have 2 balls here, and it's not actually very easy to tell which one is which. So it's always fun to use them. And if I drop that one, that's not a very fun ball. If I drop this one, it bounces much more. So you can even tell when I drop that, it makes a lot of noise. If I drop this one, it doesn't make so much noise. You're not losing so much energy into heat, light, and sound. So essentially, the main reason you have a change in thermal energy is some sort of frictional process, either frictional process because you're dragging something across the ground, or the frictional process inside the ball when it bounces. So we've applied these conservation laws now to cases where we transform the energy from one form into another, from potential into kinetic energy, for example. But we can also apply it to cases where we have collisions. And so there are 2 types of collisions, and or 2 extreme types of collisions. That's what this demonstration is supposed to be about. There's the elastic collisions, and this isn't perfectly elastic because it doesn't come up to the same height. But then there are inelastic collisions where the objects collide and they stick together, and after the collision they're going at the same speed. So by dropping this on the Earth, it's basically stuck to the Earth. The Earth will now be going a little bit faster in that direction, but this is so light compared to the Earth you just don't notice. Now, when we have a collision, like a collision between these two balls, the conservation of momentum equations that we used last week apply whether or not they stick together. So if it's an inelastic collision and they stick together and then go off at the same speed, this momentum is conserved. If they bounce off each other and there's no loss of kinetic energy, then momentum is still conserved. So to do the problem completely, you need to know both the kinetic and the kinetic energy and the momentum before and after. So this is an example of working out how much energy was converted from kinetic energy into other forms of energy such as heat and sound. And this is quite similar to a problem I think we did a few lectures ago of colliding train cars. You can see here these cars are, one of them is going to the right, one of them is going to the left. After they've stuck together, they're going quite slowly, only 0.25 meters per second, whereas before that they were both going quite fast. And remembering that the kinetic energy is a half mv squared. So if you're going twice as fast, it's 4 times the amount of energy. So we expect that most of the kinetic energy before is turned into heat and sound and maybe light, maybe some sparks. So let's work that out. So yeah, we choose our system to be the 2 cars. So we're saying this. We're ignoring the rest of the system because there's no friction. So that's the before system. That's the after system. I guess the before and after system also include the heat. After they've collided together, presumably there's some heat generated at the collision, just like there's heat generated when I bounce the ball. So initially one was going to the left, I guess, at 1.1 meters per second, and one to the right, and they had slightly different masses, or very different masses. So the initial energy, kinetic energy, was 4.7 times 10 to the 4 joules. That's it's quite a lot of energy. Whereas the afterwards, this is when they were. Whoops. Sorry, my drawing is pretty bad. I'm not going to get a job as an illustrator for children's books or anything. So afterwards, both of them are moving at a relatively small speed, and the total mass of the system was m1 plus m2, which is 6 times 10 to the 4 kilograms. 2 plus 4 is 6. And you multiply that by the square of the velocity. Minus 0.25 squared is a positive quantity, and you get 1900 joules. So rather unhelpfully, they've written that as 1,900, and they've written that as 4.7 times 10 to the 4, but that's 47,000, and this is 1,900. So there's actually not not much left as kinetic energy after that collision. So we have 47,000 minus 1,900 gives 45,000 joules has been converted into other forms of energy, into heat mostly. 96% of initial kinetic energy. This is typical of many real-world collisions. Okay. Now that was an inelastic collision. The carts came together and crashed and stayed at the same, going at the same speed. In the elastic collision, you might have this situation where one of the balls is moving. It hits the other ball, and then they both end up moving. In this particular case, if you've wasted too much time playing something like pool or something, you'll know that generally if the balls aren't spinning or doing some other sort of thing, if you have a stationary ball and you collide another ball of the same mass, then essentially the blue ball will stop and the yellow ball will keep going. And you can see that sort of intuitively, because that's the only way you can conserve both momentum and energy in this collision. If you have a more complicated collision, then it gets very, very difficult. So we're not going to do that in this course, but in general, what you would do is write down momentum conservation, which we know how to do, write down energy conservation, which we know how to do, and we can combine those together and solve for V1F and V2F, for example. So if we know the initial masses and the initial velocities, then we can use those two equations, combine them together, do some algebra, and work out formulas for that. But we don't really learn anything particularly new about the physics by doing that. But it's obviously important if you want to do a real calculation. So you'll do lots of calculations like that in later courses. Now, this final thing we want to cover here is the idea of power. So we've talked about energy, and power is the change in energy per unit time. So it's the amount of energy transformed into other forms in unit time, and that's relevant obviously for thinking about something like a light bulb or something. There's a certain amount of light coming out of there, and a certain amount of electricity that's being used. You want to know how much energy is being used per time interval. So the energy, what was this? The energy was in joules. The time is in seconds. And the energy or the work is in joules, and the energy unit of power is the watt. So 1 watt is 1 joule per second, and so let's see. So the newfangled LED light bulbs are generally use something like 10 watts or something. So there's 10 joules per second of electricity being used in those. The old-fashioned incandescent bulbs were maybe 100 watts. A small heater is 1,000 watts. Now, one of the one of the things that's kind of annoying is that, you know, when you look at your electricity bill, you know, the unit of energy is joules. So your electricity bill is you're being billed for the amount of energy you used. But as you know, the usual thing you see on that is kilowatt hours. So what they're doing on your electricity bill is taking kilowatts, which is a power unit, and then multiplying it by hours, which is a time unit, to get back to something which has units of energy. So that can actually be really confusing, you know, because people tend to then think of kilowatts as energy rather than being power. Rather than being power. Okay. So we can put this together with some of the other things we've learned about. Since the power is the energy per unit time, power can be the work per unit time, but we know how to calculate the work. The work is the force times the change in distance. So the force times the change in distance, we divide that by the change in time. We can rearrange that. So if we're pushing something along at a constant speed, the power is force times the change in position per unit time, or the force times the velocity. It's a rate of energy transfer due to the force acting on an object moving at a velocity v. So I don't think we're using that really particularly much in this course, but we're just introducing a few of these things which you will probably use later. You know, so you remember, like before, we were using the work was the force. The work was the force times the distance. That's what was going into here. And the power is the force times the velocity. So we've got, in conclusion, potential energy, gravitational, elastic, thermal, and we can use conservation of energy in collisions in conjunction with conservation of momentum, which is always important. And in some cases, we want to know the power, because that's an important concept kind of in the way you live. We use a lot of energy in our the way we live, and you need to be able to calculate that. So that's the basic energy model. These are just summaries, I think. Important concepts. Again, we didn't talk about rotational kinetic energy in detail, and we talked about work, perfectly elastic. So this is a formula we could derive for perfectly elastic collisions, but it's quite a complicated looking formula, and so I don't think we're using that much. You might come across that when you're going through the book or something, but don't worry too much about it. And we have power. Right. Okay, so as I said, this is the end of the section on mechanics, and so next week Shah, who's been running some of the tutorials, will be telling you about waves and oscillations, and so you'll probably still see me around a little bit towards the throughout the course, but hopefully things are getting easier. You know, I know there's a lot of tough concepts here for some of you, but I'm confident you can figure out how to make use of them in the future. Okay. we need the option of people being able to be distanced. It's really hard to give these lectures and just way yourself in the room.
Yeah, sure.
It's actually quite
I just find it more engaging if it's like listeners.
yeah.
It's a lot
What's the difference between watching TV and going to movies?
Yeah. Exactly. I sent you an email by the way just now regarding that question. I was quite busy last night, so I wasn't able to do it.
Oh, you sent me
The diagram.
the diagram. Yeah. I think I'm not sure why I always have some people's diagrams, either the way that it gets uploaded or the way I download it.
It's always an issue.
Yeah.
I don't know. I couldn't upload mine originally because it was like the HC something.
Yeah, what is that?
I have no idea. I think it's because I airdropped it from my phone to my laptop and then I tried dragging it. I don't know. I fixed it now. I fixed it now.
What sort of phone is that?
iPhone.
Oh, okay.
Onto a MacBook.
Yeah,
And then drag and drop, but I don't know. I've sent the right one now, so.
yeah, because I can read those files, but sometimes, some of them I can't.
Yeah. No, that's all good. All right.
Okay, yeah, thanks. Yeah, see you later.
I still haven't got a result back on my lab report. I emailed the person, but they haven't responded.
Oh.
Just wait.
Oh, okay, yeah. You emailed Cliff or?
Yeah, I have.
Oh, okay. Maybe he could be a little bit busy. I'm not
Yeah,
sure.
I guess it's just
Okay, yeah, we do have some of these problems with, TAs getting sick or something.